Let's talk about measures of spread and measures of center for two major kinds of data. The two major kinds of data we'll talk about this with are the quartile data. That's also is the stuff that's represented with the box plots, and also with the I don't know what to say it, the histogram data. Well, mm, yeah, let's just call it the histogram data because what I want to do is um, focus on how we present the data. And later on, I think I'll talk about how box plots and histograms have something to do with it. And for histogram data, um, it's not that always we have a normal curve, but we often talk about normal curves when we look at a histogram. Hey, does that look like a normal curve? You know, the bell-shaped curve. So this is what's going on. We can talk about spread and center in other contexts, but these are the two main ones. And at first, it's just memorization for your quartile data, right? For your quartile data, your box plot, right? You've got your stem from Q0, right? That's the minimum, and then your box starts at Q1, right? That's the first quarter. To remind you, that means 25% of the data is in that range, whatever it is, minimum to the quartile. Those are numbers, you know. Maybe for IQ it goes from 55 to 70, whatever the numbers actually are. Maybe it's costs of houses in a particular town and starts at 50 and goes to 100. Just depends. And then we have the first box. That's also 25%. And then we have the second box. That's also 25%. Remember, quartile 1 is here, quartile 3 is here, because the center, the median, right, that's the measure of center for this scenario. The measure of center for quartile data that's the center, right? The median is the one where you count up and down from the bottom and top, and where you meet in the middle. It's the middle data. Remember, that's not the same as the average, right? The middle of the numbers 1, 2, and 100, right? 1, 2, 100. There's 3 data points. This is the median, the center of the data. If we're going to think of this in quartile terms, the median is a measure of center for quartile data, because really the center is quartile 2. And then we've got the other whisker going up to the maximum. And again, I'll just, for emphasis, I'm going to remind you, it doesn't matter how wide these things are. They each have only 25%. In fact, the bigger they are, the less dense they are, right? If there were 100 things, there'd be 25 in each area. So they'd be spread out pretty thin in this one. Whereas here, they'd be jammed together pretty closely. So unlike every other graphic that you see in statistics, size has nothing to do with amount. In fact, it's counterintuitive. The amounts are all equal, 25% each. The size just shows you how spread out that quartile is. Oh, and of course we need the center. Sorry, we have the center. Of course we need the spread. And we're not going to go minimum to maximum because, that's too crazy. That includes outliers. So you definitely don't want to do that. Instead, we define the spread as the difference between Q1 and Q3. We give it a name. We call it the interquartile quartile range, right? Not the full range of Q4 minus Q0, but the interquartile range, I, Q, R. So spread is Q3 minus Q1. Informally, that's just the width of the box part, right? The middle, the width of the middle. What do we do with the middle in a box plot? We make the middle into a big box to say, hey, this is the middling data. There's going to be some outliers elsewhere in the skinny part, in the stem part. So the center is just Q2, and we call that the median. Okay, so there's that. I'm going to keep that on that half of the page because the other stuff is the histogram data. Right, we have our histogram. Let's make it, at least somewhat bell curve-ish. Let's say we're doing some kind of measurement in a situation where we do expect the data to come out normally distributed. Maybe it's the height of females or the IQ of Americans or something like that. Or the, I don't know, the amount of wear on a step measured in inches from the edge, right? People tend to step in the middle, so that's where there's going to be more wear, right? And remember, histogram data that is kind of normal, kind of bell-like, is usually what we see in natural situations, right? So there's sort of an underlying bell that could fit this data pretty well. The center is just the mean, right? The usual, what we usually mean by saying average, right? We mean the mean, and that's the one where you sum them up and divide by the rest. Mean is the center of histogram / bell curve data. And the spread is the standard deviation. I mean, look at the word right there, deviation. Deviation means differing from the norm, differing from the center. Lost the D there. Standard deviation, that's the spread. And literally, I mean, both of these ideas of center and spread, they literally control the picture, right? If maybe this is the distribution of, I don't know, heights of males in a certain population, and then we look at the distribution of heights in a different population, and what we find there, I'm just going to draw the bell curve. What we find there is we find a much wider but lower bell curve. Look at that. It's got a mean in the center, but the standard deviation is going to be quite a bit wider, right? That's about the length of a standard deviation. Here, the standard deviation is quite a bit less. And I do want to remind you that you always want to remember that when your data is reasonably normally distributed, we have the empirical rules, 68%, 95%, and 99.7%. So what you want to do is, I'm only going to draw one, right? The 68%. That means within one. Well, what do you mean one what? Within one spread of the center, right? Within one standard deviation of the mean. So 68% in normal data, about 68% of the data is within one standard deviation of the mean. So you have to go up one and down one, and you expect 68% of the data to be in there. That's called the rules of thumb or the empirical rules for normally distributed data. And we have further rules. If it's within 2, then you're going to have 95% of the data. And if it's within 3, you're going to have 99.7% of the data. And remember, within means both directions. So for example, let's go back to 68% within 1, right? 100% minus 68% gives you 32. But you better not draw 32 over here, because no, there's two sides. There's two sides, right? So don't forget, your leftovers are split in two. So I'll just put a scribble here, right? It doesn't matter what the center is. If we had a 2 deviation measurement, 95%'s in the center. And so more than 2 above and more than 2 below would have to share the 5% equally, 2.5% each. Same for the 3 deviations. That idea of splitting things up and looking at particular intervals and knowing what percentage is in each part, right? Like 34 here, because it's half and half. Sorry, you couldn't see what I meant by here. 34% over here, and of course 30%, 34%, on the other side. In a perfect bell curve, that's pretty much how things work out. Real data isn't perfect, but real data that's normally distributed means it's close enough you can use all those tools. That's all we mean by spread and center, right? It's median, and then the interquartile range is the size of the box. The median is the line in between the boxes, right? The median, that's the center. The spread is, okay, the size of the box, Q3 minus Q1 is the spread. Here we have the mean as the center, and the standard deviation is the spread, right? We talk about, things that are less than 95% to happen by chance. Usually we call those statistically significant. That's more of the stats 2 kind of material, but it's important to think about that stuff. Here we have, in the quartile data, we also have another way to find outliers, things far away, like statistically significantly different in the normal stuff. We don't have a test for statistical significance, but we do have a test for outliers. An outlier with quartile data is defined to be, it's greater than Q3 plus 1.5 IQR. Or less than Q1 minus the IQR, right? It's the small one, subtract, get smaller than. Let's talk about that. Oh, I don't know. I'll just put that in red. It's kind of interesting. Right, outliers. They're pretty far away. 1.5 times the IQR is how far you've got to go away, right? So just eyeballing it here, the outlier is that wide. 1.5 of them is probably, I don't know, about that wide. And then I'd have to kind of transfer that distance over and like, okay, let me go to Q3, right? And this is all rough. It does look like the maximum there is farther than 1.5 spreads from the center, not from the center, spreads from Q3. You don't measure from the center. Notice how the left side of my measurement starts at Q3 over here, right? I started right here at Q3. So it does look like Q4 is indeed an outlier. The maximum is an outlier. And it's also pretty clear when you go to the other side and go lower than Q1, no, that's not an outlier. There are no outliers below, only outliers above. With a bell curve, they kind of smooth off to infinity. There's always outliers. With actual data, you might not actually have somebody in the tail 2.5% above or 2.5% below when you're talking about the histogram normal curve data. So there you go, measures of center and spread, and a little bit of discussion about outliers, the things on the ends.